we begin to talk about complex numbers, whose importance in the study of mathematics cannot be stressed enough. A complex number, which is usually denoted by z, is a number of the form a plus ib, where a and b are real numbers, and I is defined by the property that I squared equals -1. The addition and multiplication of complex numbers are defined by a plus ib plus c plus id equals a plus c plus I times b plus d, and a plus ib times c plus id equals ac minus bd plus I times ad minus bc. Under these definitions, many properties for real numbers, including commutativity, associativity, and distributivity, also hold for complex numbers. So in most cases, we can manipulate complex numbers the same way as real numbers. A complex number z, written in the form a plus ib, where a and b are real numbers, is said to be in the standard form or the Cartesian form. This is because we can visualize z on the Cartesian plane by corresponding a plus ib to bracket a comma b. In this case, the horizontal axis is called the real axis, and the vertical axis is called the imaginary axis. This is more commonly known as the complex plane. Let's introduce more definitions for complex numbers. For a complex number in the standard form a plus ib, a is called the real part of z, denoted by re of z. B is called the imaginary part of z, denoted by im of z. Also, the complex conjugate of z is defined by z bar equals a minus ib. The complex conjugate has some useful properties, including z plus w bar equals z bar plus w bar. Zw bar is equal to z bar w bar, and z double bar equals z itself. We also define the absolute value of z as the square root of z times z bar, which equals the square root of a squared plus b squared. Indeed, z times z bar is equal to a plus ib times a minus ib, which equals a squared minus ib squared, which equals a squared minus I squared b squared, and this is just a squared minus -1 b squared, since I squared is -1. So indeed it is equal to a squared plus b squared. Properties of the absolute value include: firstly, it is greater than or equal to 0, with equality if and only if z equals 0. Secondly, if lambda is a real number, then the absolute value of lambda times z is equal to the absolute value of lambda times the absolute value of z. Thirdly, the absolute value of z plus w is less than or equal to the absolute value of z plus the absolute value of w, which is known as the triangle inequality. Note that we can express the real part and the imaginary part of z in terms of z and its complex conjugate. We write z equals a plus ib and z bar equals a minus ib, which we label as equations 1 and 2. We can add the two equations together to get z plus z bar equals 2a. So the real part of z, namely a, is equal to z plus z bar over 2. On the other hand, we may subtract equation 2 from 1 to get z minus z bar equals 2ib. So the imaginary part of z, namely b, is equal to z minus z bar over 2i. Moreover, we observe that complex conjugation corresponds to reflection about the real axis. Indeed, complex conjugation is simply negating the imaginary part, which results in negating the second coordinate of the point. which is the result of reflecting a point on the real axis. Let's do an example of expressing a complex number in the Cartesian form. We look at the number 3 plus 4i over 1 minus 2b. For this, we make use of the fact that z times z bar is equal to the real part of z squared plus the imaginary part of z squared, which is a real number. Thus, we can multiply the numerator and the denominator by the complex conjugate of 1 minus 2i, which will make the denominator real. So we have 3 plus 4i times 1 plus 2i over 1 minus 2i times 1 plus 2i, which equals 3 times 1 plus 2i plus 4i times 1 plus 2i over 1 squared minus 2i squared, which equals 3 plus 6i plus 4i plus 8i squared over 1 minus 4i squared. And that equals 3 plus 10i plus 8 times negative 1 over 1 minus 4 times negative 1, which equals negative 5 plus 10i over 5. So the final answer is minus 1 plus 2i.